Hi, everyone. Thanks for coming back. Today we have Ken Shoulders number 38, and this is just a continuation on the information that Chris Beskar, the CEO of Stevati Aerospace, had given me because Ken Shoulders was his business partner for a long time before he passed away. And we also have this letter, which is just amazing. Was from Richard
Drop you
Feynman
off and you can get an Uber back to the lake.
to Ken Shoulders.
Get your shit in one sock here.
Oh, Chip, maybe you can shut your mic off.
I will. Asshole. Just a minute, Ed. I
Okay.
got a lot of issues going on here.
Yeah, it sounds like it.
You're so fucking assholes. We are.
Okay.
Okay, so I'll just start now. So this is a letter from Richard Feynman to Ken Shoulders, California Institute of Technology, Charles C. Law Ritston Laboratory of High Energy Physics, January 31st, 1986. To Dr. K.R. Shoulders, Institute for Advanced Studies, blah, blah, blah. Okay, dear Dr. Shoulders, when you were in my office, I could not see how 10 to the 10 or 10 to the 11 electrons could be kept as a ball in a vacuum without ions. So I was skeptical and didn't let you tell me about them. I must apologize, for it has come to my attention that it is indeed possible. In a uniform magnetic field, a group of electrons rotating at the Lama precession frequency, omega equals E charge of the electron times magnetic field divided by, I think that's Lm. I'm not sure M meaning mass, it could be mass, L length, L M mass. I have to check it out. So Lama precession frequency field. So I'll read that again. In a uniform magnetic field, a group of electrons rotating at the Lama precession frequency feel, from the point of view of an observer rotating with them, a force toward the axis which would in size be equal to the centrifugal force expected from this rotation, m omega squared r. M is mass, omega is angular frequency squared, and r is radius.
Yeah.
But directed inward. Then an electric quadrupole could be used to hold them by repulsion along the axis, as long as the force away from the axis generated by the quadrupole does not exceed the previously noted confining force from the magnetic field. By adjustment of the size of the quadrupole field, the forces of confinement can be made equal in all directions, just as if there were a density of ions in a vacuum and a rotating sphere of charge is possible. The size seems to be governed by the electric field available without breakdown, but it looks like a reasonable possibility is 2 times 10 to the 11 electrons in a magnetic field of several hundred Gauss. Gauss is a measure of magnetism, like Tesla, which is Tesla's got the units of Tesla. It's a measure of magnetic density. Now that I understand how it might work, I should be glad to discuss it again anytime you wish. My informant was the physicist Curtis Michel, who told me that ions are confined this way at the Bureau of Standards. Ions are easier. The electric field needed is less, and B for magnetism, magnetic density, magnetic flux density, can be raised to, say, 15,000 Gauss. Some work of this kind was started 10 years ago at UCSD, University College. What's that? University. I think that's UCSD by a Professor M. I forget the full name. But at first, the phenomena seen were not understood. I again apologize for my skepticism, which prevented me from hearing about something very interesting. Sincerely, Richard P. Fainham.
Yeah, and when I did an interview with Chris, we talked about this letter, and basically Chris Beskar, the CEO of Stevati Aerospace, said this is the smoking gun, which is absolutely true because you have Feynman twice in this letter apologizing to Ken for not listening to what the research that he was working on. So it's something that we've gone through in the past. I just kind of wanted to bring it up again, and now we have some more information from uh, Chris Beskar, the stuff that he sent us. But this is really cool because there's some really cool pictures in here of stuff. So
Electromagnetic pulse source using fluidized electrons by Ken Shoulders. Appendix 1, June 29th, 2005. Figure 1, EVO strike with skipping on anode in xenon flash tube powered by piezoelectric generator. The piezoelectric pulse generator taken from a cigarette lighter is used to power the xenon flash tube. The EVO is that exon exonon or
Xenon, I think. Yeah.
xenon.
Yeah.
EVO is seen coming from the cathode on the left side of this optical photo and landing with a skipping action on the right side, where the anode wire is located. The inductance of the lead wire is too high for an immediate dump of EVO energy, resulting in a cyclic process for the energy transfer. Photo using a macro lens on the camera and 35mm film. The dimension of the photo from left to right side is approximately 0.01 inches. Okay, figure 2, multiple EVO strikes with skipping on the anode in xenon flash tube powered by piezoelectric generator. This view is similar to figure 1, with the exception of multiple smaller EVOs arriving that do not skip on the anode. Only the largest strike seems to skip. This is largely due to the increased charge induced in the electrode, resulting in a greater voltage swing on the anode, causing rejection of the approaching EVO after first strike.
Wow, amazing.
Okay, figure 3, what's that? A scanning electron microscope.
Yeah. Yeah.
Scanning electron microscope of EVO skipping across film of aluminium on glass, or aluminum if it's for the American version. An EVO is seen coming in from the top of the photo in this scanning electron micrograph and breaking up as it proceeds across the thin aluminium film. There is a distinct hopping action seen as the EVO progresses. The split then occurs as the breakup cedes and some branches die completely. Figure 4, scanning electron microscope magnified view of EVO breakup. This view is an extension of the lower portion of figure 3 taken at higher magnification to more clearly depict the interaction with the aluminium film coating on the glass substrate. Pits in the aluminium can be seen as the EVO tumbles and hops over the surface. Such erratic motion causes intense electromagnetic radiation in the submillimeter portion of the spectrum as the EVO is moving at approximately 1/10 the velocity of light.
That's pretty fast when you think about 1/10 the velocity of light too, right?
Yeah. Figure 5, pinhole camera side view of dual EVO flight through vacuum. Coming from the EVO source at the lower portion of the pinhole camera image, the EVO is seen to follow a helical pattern of motion and decomposing into individual electrons as it moves at a rate of 1/10 the velocity of light to the top of the photo. The length of the EVO run in this photo is approximately 0.1 inches. This type of charged motion produces a chirped spectrum of radiation sweeping from higher to lower frequencies.
Pretty incredible to see the helical pattern of that. Hey, this is the one that I thought was most significant.
Figure 6, pinhole camera end view of EVO flight showing somewhat regular instabilities of vacuum flight and a thrusting type of propulsion. The EVO source is located at the center of the photo, and the EVO flight is directly into the pinhole camera, showing a kinky, spiraling motion. The turn radius is smaller than can be accurately measured in this photo, but is in the order of a few micrometers, giving a turning time of a fraction of a picosecond. I think a picosecond's 10 to the 9, 10 to the 12. I can't remember. 10 to the 9 or 10 to the 12. Anyway,
Yeah, it's pretty
the
small.
10 to the minus 12 rather. Or 10
Yeah.
to the deflection energy source is certainly located within the EVO itself and does not come from externally applied potentials due to the short time deflection requirements. This resultant motion gives rise to a wide emission spectrum.
And look at the pattern of this one. Wild.
Figure 7, scanning electron microscope of EVO exotic vacuum object launching source from chromium film deposited on a glass substrate. This unique diagnostic technique shows that electrons flow toward the center launching point where the EVO departed into a low pressure gas environment and on the cathode, on the anode. The electron flow direction can be seen due to the momentum imparted to the fluidized chromium and moved inward instead of outward on each of the current feed branches. The thinned region of convergence at the center is where the EVO lifted off the surface for the anode flight. Without the use of high resistance chromium film, this effect cannot be seen.
So how did he figure that out? How to do this, right? He was a genius.
Figure 8, scanning electron microscope of EVO strike on a chromium coated glass substrate used as an anode target. This photo is the anode of the cathode shown in figure 7. What is evident here is that the EVO arrived from the left side of the photo and moved toward the right as it skipped along the surface, taking some chromium film with it. Dark streak on the left is actual and apparently caused by the approaching EVO modifying the chromium as it skims the surface looking for a landing spot. This data further reinforces the notion that EVOs do not necessarily stop completely upon first contact with an anode. There are many motional aspects to them, leading to diverse radiation patterns. Figure 9, scanning electron microscope of dual hopping EVOs attempting a landing on an anode. 3 strikes of the same dual EVO exotic vacuum object are seen here while attempting a landing on an anode. The circles drawn around each attempt is shown in the photo. Due to the somewhat rare occurrence of dual EVOs, it can be surmised that the strikes seen are due to the same dual EVO lightly skipping over the surface for a final strong impact. This is the reverse order from what was shown in earlier figures, where the most energetic strike came first. The direction of an EVO travel can be determined by the direction of the motion imparted to the fluidized material in strike number 4, shown in figure 10. Okay, figure 10, scanning electron microscope of 3rd and 4th dual EVO strike on an anode. As an extension of figure 9, this scanning electron microscope photo shows the 3rd and then 4th, final 4th strike on an anode. It can be said with some assurance that the EVO landings are multiple events leading to a spectrum stretched toward lower frequencies instead of depositing all of their energy in the X-ray and optical end of the spectrum. This low frequency energy burst leads to greater damage to electronic devices, although it does not transmit through shielded structures, as well as short wavelength photon radiation.
You can really see that 4th strike, how it's a lot bigger of a hole that it created.
Yeah. 4th strike there. And
Yeah, the bottom
strike
one.
there.
Yeah.
Figure 11, front view of plasma flash caused by sequential arrival of 2 EVOs having a diameter of 10 micrometers. One 10 micrometer diameter EVO strike on a stainless steel anode causes only an imperceptible plasma flash that would not be recorded by the method used here. When the first EVO arrival causes a small plasma to be formed, that is then struck by another EVO arriving about 1 picosecond later. The flash is many times larger, as shown in this self-illuminated photo, taken along the path the EVO is traveling. The volume of the flash is over 1 cubic centimeter from the single pair of EVOs used in a particular way. Not many combinations of use produce the same effect.
It's really bright.
Sorry?
It's a really bright flash, right?
Yeah. Figure 12, side view of plasma flash caused by sequential arrival of 2 EVOs having a diameter of 10 micrometers. This side view photo is taken of the image shown in figure 11. It is the same each time and is not a function of apertures or other plasma limiting devices, but rather caused by a fundamental interaction. What the hell? I'll just get that up. I think, anyway. It is the same each time and is not a function of apertures or other plasma limiting devices, but rather caused by a fundamental interaction between the plasma produced by the first EVO arrival and the second EVO. The light output difference between this complex interaction of a simple EVO strike on metal is in the order of 1,000 times greater due to a close approximation to something like an impedance match between the second EVO and the plasma.
That's interesting.
It should be borne in mind that it is undesirable for an EPM, electromagnetic pulse application, to put much energy into the visible spectrum when a lower portion of the spectrum is beneficial for electronic device and ordnance construction.
Interesting. When he talks about this impedance match, that's something that we do in audio equipment, and we design transformers to do that. And when the impedance match is perfect, then you have the 100% energy transfer function. So that's why he was kind of talking about that. This next one is really cool, hey? We've seen this one before, I think, but not in this big of a format.
Figure 13, edge view of multiple EVO strikes on air on an aluminium foil coated with silicon carbonate, or SiC. I wonder, silicon carbonate or something like that.
Carbonate, maybe? Yeah.
Silicon carbonate. Okay. And epoxy mix. The multiple EVO strikes are caused by the induction coil driven electrode being scanned along the top side of the foil with a spacing of about 3/4 of an inch. In some regions, the EVO penetrates the 0.02 inch thick coating and 0.001 inch thick foil, carrying the fluid out the backside, flowing as a flare in the photo. In other cases, the EVO just penetrates the coating and foil and then reverses direction, carrying the fluidized silicon carbonate, or whatever that is, SiC, out the entry direction with high velocity. The ability to penetrate is tied to having an electrical impedance match for the EVO upon emergence into the space beyond the foil. Deep penetration of materials depends upon having a form of impedance match between the EVO and the material being bored. The EVO matches the impedance of earth and concrete structures. It does not match highly conductive metals. So, Eddie, you're also saying that these came from Chris Beskar. So these documents are not freely available.
I think that he might have that available now to the public, but originally this was all the stuff that we're going through. This was a part of it. Yeah.
Figure 14, scanning electron microscope of high velocity deposit on silicon carbonate or SiC on an aluminium target from an EVO boring through a layer of SiC on aluminium.
It's silicon carbide.
Sorry?
Silicon carbide.
Silicon carbide. Okay.
Yeah,
Yep.
that's what we had said. Yeah.
When a plate of aluminium is placed below the structure shown in figure 13, the fluidized material caused by the EVO passage can be driven deeply into the plate. In this instance, the splatter is controlled by the process of spread only laterally and does not strike the foil above it. The fluid slug size is typically 20 micrometers in diameter and 100 micrometers long, and has a penetration depth of about 100 micrometers. If such a slug of material were to strike the enclosure of an electronic device, the internal damage from both particles and radiation caused by the entrained EVO would be severe. Going towards the end now. Figure 15, scanning electron microscope of backside of an EVO borehole. EVO entry side of an aluminium foil shown in this photo is coated with a layer of silicon carbide and epoxy cement. The EVO is generated as shown in figure 13. Although there are a variety of borehole exit strategies used by EVOs, most of them are clean holes like this. It is anticipated that larger quantities of fluidized electrons, properly configured, could bore clean holes into the earth and into ensconced bunker cavities, releasing enormous energy into the bunkers encountered.
Sounds like a high-tech bunker buster bomb, actually, is what he's just described there. That's interesting.
Figure 16, pinhole camera image of X-rays reacting inside of camera and penetrating thick walls. On the left and right side of the image is a pair of dark vertical lines due to energy absorption of X-rays by these energy analysis electrodes. Normally, the field view is clear of this effect because the camera is designed to image objects beyond 5 millimeters from the nose. But due to the source of energy being caused by a closer EVO strike on the camera itself, the deflectors show. The white image in the center is the normal electron image from an EVO coming straight at the camera. This image signifies that an EVO landed on the 0.04 inch thick camera nose, producing an intense effect, yielding X-rays detected by the micro-channel plate electron multiplier in the camera. The overall measurement records a high-energy EVO strike capable of destroying a large number of shielded semiconductor devices. There we go now. Figure 17, pinhole camera image of particles ejected from rear of aluminium foil. When an EVO strikes the front of an aluminium foil without a hole in it, there is an emission of chunks of material from the backside that can be detected using a microchannel plate electron multiplier operated at a gain of about 10. The speckle image shown is for a mild EVO attack. When allowed to maximize for a 10 micrometer EVO strike by adjusting landing bias voltage, the 0.001 inch thick foil is punctured and a spray of metal particles strike the multiplier, causing damage. The likelihood of severe damage to semiconductors is high when this process occurs even at low level of activity, as it is usually accompanied by X-ray generation when thicker targets are used.
So this is interesting. The 1 thou thick foil is punctured and a spray of metal particles strike the multiplier, causing damage. Just before that, it's talking about the bias voltage. So by adjusting the landing bias voltage, that's really interesting. Bias voltage is something that we use in vacuum tubes to actually make them turn on. So it's interesting that he used that terminology there. And the last one.
Okay, figure 18, text copied from EVA Electrovalidium or Exotic Vacuum Object, A Tale of Discovery by Ken Shoulders, 1987.
Yeah, his book.
Guide,
Yeah.
pages 847 and 848. The apparatus that was first used, sorry, I'll write that again. The apparatus that first showed the effect is shown in figure 6.1 and is the apparatus in which most of the streamer work was done. When streamers rise up from the center electrode and strike the top, they turn and run radially on the flat surface of the cover glass. The run is not entirely straight as they approach the cylinder wall, but at times there is a fair approximation to a radial line. When this happens, the line is viewed from the end in the plane of the top. A bright scintillation can be seen. If a piece of white paper is placed around the cylinder, many scintillations and streaks can be seen. In order to make the effect more obvious, I cause streamers to run in long glass tubes by exciting them with short bursts of radio frequency at a frequency of between 1.7 and 5 megahertz. About 10 cycles of radio frequency, RF radio frequency, was the minimum that I could conveniently generate. Under the conditions that produce small, thin streamers, these streamers would run for a distance of 2 inches or so on the inside of a 3 millimeter glass tube without turning. They then would suddenly deflect a small angle and then run straight again. By looking at the deflection point, it could be seen that the deflection was caused by something on the surface. I put small grains of various substances on the surface to see what the effect preferred. Silica sand was the winner. The sand had bright faces or facets, and I reasoned that it was this optical surface that caused the turn. I also applied the sand to the center electrode and found that it would cause the launching of a streamer whenever the conditions of angle and field were correct. There was no way to control the process with the apparatus used, and the effect was strictly a statistical one. Someday we will get a control on the effect, and it may prove to be a laser-like process, generating the beam that the EV then rides upon. If such, so that's the EVO, the EV or the EVO rides upon. If such guidance does become practical, there is a good chance for focusing enormous energy density from multiple surfaces that are a lot easier to make than conventional lasers.
That's a pretty interesting statement there, the last part. I guess they're trying to be able to focus them like lasers, essentially. Focusing enormous energy densities from multiple sources. Wow. So Ken is basically trying to figure out what happens with these EVOs, with these different experiments. One of the things I was going to say was most of everything that he's doing is looking at EVOs, like that one picture with the EVOs coming into the aluminum foil and then having streamers come out the other side, or what looked like rocket thrust, basically. So he's looking for different ways to use them for technologies such as propulsion. One of the things that we do in this group is we talk about EVOs in the form of consciousness. And so that is completely different to the experiments that he's doing here. And we know that, and I've got slides from Stavati that talk about how EVOs are connected to our consciousness and how every time we meditate, there's an EVO. When we dream, we've got an EVO. And we always have to remember that Ken Shoulders is talking about EVOs in again, the context of energy densities and packing them to see the different things that can come out of there. But the other thing that's happening with EVOs is you can consider the energy density, but you could also consider that being information. So an EVO is actually a package of information as well too, and that's why when you meditate or you dream or anything like that, you're actually creating these things. So very, very interesting. Does anyone have any comments before we shut the recording off about the cool pictures that we just saw? No? Okay, well, maybe we can finish shut the recording off, and thanks everyone for coming again.
Thank you very much. Thank you, everyone. I hope you have a wonderful rest of the day. Cheers. Take care. Bye.
Yeah, thank you.